computability, and the Euler characteristic. Right? And then, of course, there's a classification of finite simple groups, which is just a big list of all the possible finite simple groups. But right, in all these cases, you get some kind of real understanding about the objects in these classes and how to tell if they're isomorphic to each other or not, right? And each of these characterizations, right, each of these classifications is somehow simpler than the abstract idea of isomorphism, right? So the dimension, right, it's very easy to check if two dimensions are the same. It's much harder to sort of think about, okay, how am I actually going to define an isomorphism without thinking about, something about the actual structure. What's a characterization? So a characterization, you have maybe some object or some property, right? And it's got some definition that you came up with originally. And a characterization is some other list of conditions, which is different from the definition you started with, but it's equivalent, right? And again, it should somehow be simpler, right? It shouldn't just be rephrasing the definition. It should be some simpler condition to check, right? So maybe it has like connections with other areas that are interesting. It's easier to check whether the different conditions hold or something like that, right? So I've got 3 examples here. Also, everyone should know these, right? So, right, if you define a number to be prime, it's prime if and only if whenever it divides a times b, it either divides a or divides b, right? So this is different from sort of the standard definition of primeness, but it's equivalent, right? And it tells you something interesting about prime numbers. A square matrix is invertible if and only if it has, so I think I wrote 0, if it's determined as non-zero. Right, so to see if something's invertible, right, the definition says you should look for a matrix that's its inverse. But this characterization gives you another way to check, right? You just compute the determinant, see whether it's 0 or not. And the last one is an abelian group is orderable if and only if it's torsion-free, right? So if you think about this, if you want to come up with an ordering on an abelian group, it's sort of not necessarily clear how to do that, right? You'd have to sort of, to check if something's orderable, you sort of think, oh, maybe I have to start checking all these different orderings. But actually, all you have to do is check if it's torsion-free, right? And that's somehow simpler than looking for an ordering. Right, so these characterizations all give you some kind of interesting connection, or they simplify the thing that you care about, right? So the idea is you've got some property, you don't really understand it, but if you can characterize it in a simpler way, then that helps you understand the property. So those are the sort of 2 general goals of a lot of mathematics, and we'll be talking about sort of analyzing those kinds of things. So let's think specifically about classifications by invariance. So the idea is you've got some class of objects, which we'll call C, and you've got some equivalence relation like isomorphism between these objects. And right, a set of invariants for this class is a map, right? It takes objects in C to these elements of lambda, which are the invariants, right? And what should happen is you should be able to tell, right, if it's invariant. So if 2 things in C are equivalent, right, then their invariants should be equivalent. So, right, basically things that are sort of the same should get the same invariance, right? And, often, right, so for something like a vector space, the invariant is the dimension, right? And then the equivalence relation on the invariance is just equality. But if you're doing something like, right, if you're looking at like homology, right, then your invariants are groups, and the equivalence is isomorphism of the homology groups, right? So you might have to have an equivalence relation on this space of invariants. And what we really like is what's called a complete set of invariants, right? And this is where the invariants actually determine the original object, right? So 2 objects are isomorphic or equivalent in whatever way, if and only if they have exactly the same invariants, right? And it's both ways. If they have the same invariants, then they're actually the same object. And right, so we can think of this as sort of a characterization of these objects. And if you're going to have a good characterization, then somehow the construction of these invariants, right, and the determination of when 2 invariants are the same, it should somehow be relatively concrete. It should be simple, whatever that means, which we're gonna say sort of what it might mean later. But the idea is, right, is the invariant should somehow simplify things, right? They should give you some kind of understanding of these objects, right? And we'll give sort of an example of a good characterization and then 2 examples of bad characterizations. So a good one is the class of vector spaces over some field F, right? So given a vector space, right, you assign this invariant the dimension. The dimension is a cardinal, right? So the space of invariants is the space of cardinals or sizes, right? And the point is that the dimension of a vector space is relatively easy to find, right? So remember in the previous slide, I said, the construction of the invariant should be relatively concrete. It should be simple. Well, I think we'd probably all agree that the finding the dimension of a vector space is a relatively simple thing to do, right? This is a complete invariant, right? Vector spaces are the same if and only if they have the same dimension. And the equivalence relation on the invariance is just a quality, which is also very simple and concrete, right? So this is a good classification, right? Because we've got a simple way of assigning invariance to the objects, which are vector spaces, right? So this is a good classification. Now we'll do two examples of sort of bad classifications, which say why this idea that things should be concrete and simple is very important, right? So let's look at the class of graphs. So that should be to each graph G, right? One invariant you could assign is just the graph itself. So the invariant of a graph just is the graph. And this is technically a complete set of invariants, right? Because, you know, G is isomorphic to H if and only if their invariants are isomorphic, which are G and H. But this is obviously not a good classification. So we should say something about why is it that it's not a good classification, right? It's sort of obviously not good. Well, it's easy to find the invariants, right? The invariant of a graph is just the graph. So you don't have to do anything to find the invariants. The problem here, right, is that telling whether two invariants are the same is hard, right? Two invariants are the same if the two graphs are isomorphic, and that was just the whole problem in the first place, right? So this is sort of a bad classification because it doesn't simplify anything, right? You sort of reduce the problem to itself. So this is a case, right, where the equivalence relation on the invariant should be simple. Well, we can solve that, right? So the other thing we could do is we could say if we've got a graph G, the invariant I'm going to assign is the entire equivalence class of all graphs isomorphic to G. Right? This is a complete set, right? G and H are isomorphic if and only if their equivalence classes are the same. And I've solved this problem from before in the sense that it's very easy to tell if two invariants are the same, right? The G, right, just asking, is the equivalence class of G equal to the equivalence class of H? That's just our two things equal. But now the computation of the invariance is very hard, right? If I give you a graph G, to find the equivalence class, you'd have to find all the graphs that are isomorphic to G, right? So again, you have to decide whether things are isomorphic, and I haven't simplified anything, right? Now, again, to sort of compute the invariant, you have to solve the problem I wanted to solve. So this is a case, right, where the computation of the invariance is the thing that's very complicated. So, right, this is sort of showing, right, you've got these two classifications that are really not, they're horrible classifications, right? They don't actually simplify anything. And I show that it's important, right, first of all, that the equivalence relations are nice, and second of all, that the computation of the invariance is very nice and concrete. So here there's some obvious questions that we could ask, right? So specific questions. So is there some good characterization of graphs up to isomorphism, right? We gave two bad characterizations, but could we come up with a good one? And we had this classification of the vector spaces. Is this the best possible classification of vector spaces? Or is there somehow an even simpler one? Right, so these are sort of informal questions because we haven't said what it means to be good, what it means to be the best one. We'll sort of get to that and come up with formal ways of saying what those means. And so more general questions, right? How do we do that, right? How do we measure how good a characterization is or a classification is? Or how do we even show that a class of objects can't be characterized or can't be classified, right? And so this is where these tools from computability theory and descriptive set theory are going to come in to say what it means to be good or simple or things like that. And so from now on, we're going to deal only with countable structures, countably infinite structures. There are ways of dealing with uncountable structures, but sort of the basic tools of computability theory and descriptive set theory are really made for dealing with countable structures. So everything will be countable from now on, even if I don't say it. So we need to sort of build up a little bit of formalism, but it's going to be still somewhat simple in a very topological language. So I want to fix a countable set, like maybe just the natural numbers. And this is going to be the domain of all the objects that I'm going to talk about. And I want to fix a language. So what do I mean by a language? Well, basically, I'm going to fix some sort of names for functions and names for relations and names for constants that all the objects I'm going to talk about are going to have, right? So if I want to talk about groups, then the functions and relations and constants, I'm going to have like a group operation, I'm going to have the inverse operation, and maybe a constant for the identity, right? So that's my language, is I have the language of groups, right? The group operation, the inverse, the identity. If I wanted to talk about fields, right, then I'd have an addition and a multiplication operator. If I wanted to talk about graphs, then I would have an adjacency relation, right? So the language is just sort of what are the things that the objects I'm talking about have, right? What kinds of functions do they have? What kind, right? And this natural numbers that I'm choosing, this domain, basically is going to be what's the underlying set, right? So I'm going to talk about various different groups or graphs or whatever, and the domain is going to be the natural numbers, right? So it's going to be a graph on the natural numbers, or it's going to be a group on the natural numbers, and the group operation might not be the normal natural number operation, right? So it could be that the group operation applied to 2 and 6 is actually 10. Because that's just the domain happens to be the natural numbers as objects, but they're not really playing the role of the natural numbers. They're just an infinite countable set. So if there's a topological space of all the structures in the particular language I've chosen on my domain. And this is a topological space. It's a Polish space, which means that it's separable, it's complete, it's metrizable. For example, if there's only relations, right, if there's no functions around, so if I'm talking about, say, all the space of all graphs, then this looks like the Cantor space. And the basic Clopin sets are determined by atomic facts, right? So if I think about the language of groups, I get a Clopin set by saying all of the groups with AB equals C, right? So every group with AB equals C, that gives me a Clopin set of all sorts of groups. And this topological space is called the models of L, so the models of my language. Okay, so I've got a topological space of objects. If I have two Polish spaces, right, then I can talk about continuous operators between them, right? So this is just the inverse of every open is open. I can talk about the Burel sets, right? So remember, in a topological space, the Burel sets, I start with the open sets, I take their complement, so I also get the closed sets. I can take countable unions, and I can take countable intersections. Right, so I build up, I take the open sets, I take the closed sets, I take unions of closed sets, I take intersections of open sets, and I can take unions of intersections of open sets, and so on, and build up this collection of all the Burel sets. And the idea is that the Burel sets are sort of sets that are built up piece by piece, right? So they're sets that have some kind of structure. And then, a sort of generalization, right, a widening of the continuous functions is the Burel operators. So an operator is Burel if every time I take an open set, its inverse image is Burel. So this is still, these operators, right, are still sort of nicely defined in some way. They're still somehow concrete, but they're a little more general than just the continuous functions. And the intuition is that if you have some kind of reasonable construction, a reasonable construction is probably going to be Burel, if not even simpler, right? A lot of reasonable constructions are actually continuous. So for example, right, the computation of the dimension of a vector space, this is a Burel operator that takes a vector space to its dimension. So we're going to sort of think about Burel sets as being relatively simple sets, right? Relatively concrete. We're going to think of Burel operators as being relatively concrete operators between topological spaces. So the most general setting is if we're thinking about we have two equivalence relations, right? We have two topological spaces, X with an equivalence relation E and Y with an equivalence relation F. We can come up with some kind of reduction, right, from X to Y, right? So this is a Burel operator that takes things, right, elements little x to 5x and little y to 5y. And they sort of, you should think of it as assigning invariants, right? So basically you assign invariants to things in X, and the invariants take their values in Y, right? And if you remember before, right, this is just basically the same condition that we had that said that Y is a complete set of invariants for X. But now what we're asking specifically is that the operator is a Burel operator, right? So the way of assigning invariants to things in X is concrete and simple, right? So we think of this as a Burel classification of X up to E using Y as the complete set of invariants. So this is the general setting, which we won't really talk much about the general setting, but the idea, right, is there's classification results, right? So classification result is when you care about some X and you show that X can be classified by Y for some Y that's fairly simple, right? So again, vector spaces, right, you care about the vector spaces, and the vector spaces you reduce to the Polish space, the natural numbers, together with infinity, right, and the equivalence relation is just equality. So this is a classification, right, where you reduce the thing you care about to something simpler. And then there's sort of anti-classification results, right, where you care about X, and what you show is that you have some fairly complicated Y, and you can reduce Y to X, right? So if Y is reducible to X, and Y is very complicated, then this means that X is very complicated, right? Because if you could sort of any understanding of X gives you an understanding of Y, right? Because X is invariance for Y. So sort of whether you're getting a classification or an anti-classification result basically depends on which side of the reduction the space you care about sits. Right, so we said we're going to care specifically about these structures. So let's think of these X and this Y as being all the models in some class C and all the models of some class D, right? So we have two classes of structures, like maybe one is graphs and one is groups. And we're looking at the class of all groups and the class of all graphs. So we say that the class C is Burel reducible to D. Basically, we just take the definition from before, right? So there's a Burel operator that takes things from the class C, and it gives you things from the class D. And anytime you take two things in C that are isomorphic, the things that you get in D are also isomorphic, right? And that's if and only if. So basically, it transforms, right? A Burel reduction transforms structures of one kind into structures of some other kind in a way that maintains the isomorphism relation. And right, you should think if C is Burel reducible to D, then that means that that D is at least as complicated as C, right? Or C is at least as simple as D is, right? Because, for example, if you had any kind of complete set of invariants for D, then you could pull them over to get a complete set of invariants for C. So, right, an example, so if you take D to be the class of vector spaces, right, then you get actually a set of invariants for C, right? So the set of invariants for C, what you do is you turn a thing in C into a vector space, and then you take the dimension of that vector space, right? And if that reduction is a Burel reduction, right, then the computation of the dimension of phi of M, that's a Burel computation, right? So basically anything reducible to the class of vector spaces has a nice set of invariants, right? So this is why you should think of, anything reducible to something is simpler than that. For anti-classification results, right, the sort of strongest kind you could get is this, and there are sort of these examples of really strong anti-classification results. So you say that a class C is on top for Burel reducibility if it's as complicated as any other class of structures, right? So it's on top for Burel reducibility if anytime you take any other class D, D is Burel reducible to C, right? So C is like maximally complicated among classes of structures. And there are examples of things that are maximally complicated in this way. So this is sort of this original paper of Friedman and Stanley who introduced this whole idea of classifying structures. And they showed that graphs are on top, right? Linear orders are on top, groups are on top. They had some other examples as well as things like trees. We know that fields are on top. For something like graphs, this has been sort of known for a long time as sort of folklore, the idea that graphs are as complicated as anything can be. And the idea about proving something like this, right, is that so say you want to prove that graphs are on top for Burel reducibility. What you have to do is you have to come up with a transformation from other structures into graphs so that, right, anytime the two structures are isomorphic, the two graphs are isomorphic. So the graph has to somehow code this other structure in sort of a faithful way. So you end up sort of saying the elements of the structure turn into vertices of the graph, and then you put these special widgets to show the relations between everything, and sort of a complicated construction, but not actually that. Sorry, I mean, it's got some details, but it's not a complicated construction, right? So these are, and what this means, right, is that you can't come up with a good classification of graphs, right? There's no good understanding of when two graphs are isomorphic, because if you did have a good understanding of when two graphs are isomorphic, then you could understand whenever anything's isomorphic, right? So it's basically, you can't do it because if you could do it, then you could do everything, right? And then you have to show, there are actually hard problems, but yeah. So this is an anti-classification result, right? So graphs, linear orders, groups, there's no good classification of these things up to isomorphism. One case that's still not understood very well is the case of torsion-free abelian groups, right? So before when I said groups, I meant non-abelian groups potentially. But if we look at torsion freewheeling groups, this is still not very well understood. So Huerth, Kekris, and Thomas have done a lot of work on this. One of the best results is this sort of looking at them rank by rank. So the torsion freewheeling groups of rank n+1, these are not reducible to the class of torsion freewheeling groups of rank n, which is one less. So basically what this means is that as the rank increases, it gets harder and harder to classify torsion freewheeling groups, right? So it gets strictly harder and harder as the rank goes up. All right. One way of thinking about this is, right, if I had a set of invariants for groups of rank n, that couldn't give me a set of invariants for groups of rank n+1. We still don't know the answer to the sort of general question, which is, what about just torsion freewheeling groups in general? Are they on top for Burel reducibility? That's still an open question. And sort of one of the key open questions in this sort of area of classifications. So we can say something about this question by sort of changing our perspective a little bit and looking at a different way of measuring the complexity of a classification problem. So if I fix, right, again, a class C, there's this set iso of C, which people generally call the isomorphism problem, which is the set of all the pairs m and n that are isomorphic. And we can ask, how complicated is this set? Right, so we're thinking of this set as a member of a Polish space, right? The Polish space is the pairs of structures. And when I say how complicated it is, right, the first question you can ask is this Burel, right? Remember, Burel things are relatively concrete. Non-Burel things are somehow less concrete, right? So if the isomorphism problem is Burel, that means we have some kind of concrete understanding of when two things m and n are isomorphic, right? And if it's not Burel, that means that we don't really have a concrete understanding. But we can also be more specific, right? If it is Burel, we can say exactly, we're going to come up with sort of a way of measuring exactly how Burel something is. And this, we have to introduce sort of another type of reduction. And before we use Burel things, right, now we're going to strengthen the, we're going to ask for continuous things. And we get something called the wage hierarchy. So the wage hierarchy is definable on sort of all sorts of different spaces, but we'll be talking about the wage hierarchy on the models and pairs of models. And basically what you say is that if you have two sets A and B, then A is wage reducible to B. If there's a continuous function, f, right, f takes things in A and gives you things in B. And whenever you take it takes things from that might be in A and gives you things that might be in B, right? And anytime you get something in A, you should get something in B. And if you get something that's not in A, then you should get something not in B. So you think of f as sort of, f helps you translate between the question of asking, right? It lets you reduce the question of asking, is something in A, to the question, is something in B, right? Because if I like, imagine that I knew when things were in B and when things were not in B, then I could figure out when things were in A and not in A, because if I have an X, right, and I want to figure out is X in A, I can find f of X, ask if f of X is in B, and then if f of X is in B, X will be in A, and vice versa, right? So it reduces this problem of asking, is X in A, to the problem of asking, is f of X in B, right? So again, you should think of it as saying, right, A is reducible to B. That means that A is simpler than B. And right, of course, if something is reducible to something else, this is a continuous function. So if B is open, then A is going to be open, right? So it's sort of, it's downwards closed under openness. And then, right, so you can sort of think of the complexity is starting with the open things, and you have the closed things. And then, right, remember, Burel things are built up by countable unions and countable intersections. So you can sort of think of like, how many times did I have to do that to get the set I care about, right? So you start with the open sets, the closed sets that are sigma 1 and pi 1, we call them. And then if your countable union of closed sets, right, that puts you up to the next level, that makes you sigma 2. If you're a countable intersection of open sets, that puts you up to pi 2, right? If you're a countable union of pi 2 sets, that puts you up to sigma 3. And so it's just sort of how many times do you iterate this taking unions and taking intersections, and that determines your level of complexity, right? So this notation like sigma 2, sigma 3, there's sort of an older notation where people write sort of f sigma or g delta, and these really are the same thing as sigma 2 and pi 2. So if you're familiar with f sigma and g delta, this will help give you some sort of intuition of what this hierarchy looks like. So this is a way of measuring, right? Not just is something Burel or not Burel, but sort of where does it live in this hierarchy of Burel sets? How long does it take to build it up, right? And things that are higher up, right, in this hierarchy are things that take longer to build up, so they're somehow more complicated. And so we have the Burel sets, right? They're divided up. The next step above the Burel sets is what's called the analytic or sigma 1-1 sets. So these are projections of Burel sets, right? So your sigma 1-1, and right, A is sigma 1-1 and A is a subset of a Polish space X. That means that there's a product space, right? So you can take X cross Y, and there's a Burel set in this product space, and it projects down to get you A, right? So you can think of this as like, also like, maybe if you're the image of a Burel set, then you might be analytic, things like that, right? So it's a level up from the Burel sets. It's still something that's got some kind of description, but the description is more complicated, right? And so sigma 1-1 is the projection, right? The complement of that is pi 1-1. So there's sigma 1-1 and pi 1-1, and those are both sort of above all the Burel sets. So, right, you should think of a Burel set as anything you can define in a way that uses just quantifiers over elements of countable sets, right? So quantifiers over like natural numbers. You say there exists an algorithm, right? There's countably many algorithms. You say there exists a group element, things like that, or for all group elements, for all natural numbers. Quantifiers like that, those let you build up Burel sets. But if you ever want to, in the specific class, right, where you are in the hierarchy basically counts the number and type of quantifiers you used, right? So if you say like, there exists an X for all Y, there exists a Z, that's 3 different quantifiers, and that counts up where you are in the Burel hierarchy. A sigma 1-1 set, you should think of as a set you can define with existential quantifiers over subsets of countable sets, along with whatever quantifiers you want over countable sets, right? So you can use whatever quantifiers you want over natural numbers and so on, but you're only allowed to use existential quantifiers about subsets, right? So for example, if you wanted to say there exists a subset of natural numbers, you're allowed to do that. But you're not allowed to say for all subsets of natural numbers. So the isomorphism problem, ISO of C, this is always sigma 1-1. And this is because A and B are isomorphic if there exists a map from A to B that's an isomorphism, right? So the map is one of, right, there's uncountably many maps. So this is one of these quantifiers that you're only allowed to use existential quantifiers to get something sigma 1-1. That's fine, right? You can say there exists a map. And then to ask if it's an isomorphism, that's quantifying just over elements of A and B. And those are quantifiers you're allowed to use and still be Burel. So the isomorphism problem is always sigma 1-1, which is, right, so you've got the Burel sets, and isomorphism problem is sort of the next level up always. Now, if you want to show that something's, for example, not Burel, then you have to use this idea of completeness. So if you're familiar with like computational complexity theory, like P versus NP and stuff, this is a very similar idea, right? The definitions are sort of almost the same. So if you've got one of these complexity classes, let's call it gamma, and you've got a set A, then you say that A is gamma hard if anytime you have something in gamma, gamma is reducible to A, right? So this is, again, is sort of a measurement of saying that A, among all things in gamma, A is the most complicated, right? Because anything in gamma, A is at least as complicated as that is. So basically, you can think of it as sort of like any problem you have that's of complexity gamma, A can solve that problem. If A is also in gamma itself, then you call it gamma complete. So if you're gamma complete, that means you're exactly as complicated as a set in gamma can be. And Friedman and Stanley showed if you have something that's on top for Burel reducibility, so this was this previous idea of complexity, then the isomorphism problem is sigma 1-1 complete, but we have to use Burel reductions rather than continuous. So basically, right, there's some connection between these two complexities, right? Somehow on top for Burel reducibility sort of more strong than talking about the isomorphism problem. But when we talk about the isomorphism problem, we can say something about torsion-free abelian groups. So the isomorphism problem for torsion-free abelian groups is sigma 1-1 complete, right? So that means it's not Burel, right? The isomorphism problem is not somehow concrete or easily definable. It's actually quite complicated. So you should think of this as a non-classification result, right? It says that there's no good classification of isomorphism for torsion-free abelian groups, right? In some sense, the simplest way to say that two of these groups are isomorphic is to just say, you know, there exists a map from one to the other that is an isomorphism, right? Every time you take two group elements, you know, that's sort of the simplest definition of isomorphism, right? There's no simpler way. Now I want to say something about how like, I won't give the proof, but I'll say something about like what do you need to do to prove this. And right, so I won't get into the actual group theory, but what you need to do is you start with a known set. In this case, what they used is the set of trees that have an infinite path that you know is sigma 1, 1 complete. So you start with something that you already know is very complicated. And then you reduce that to the isomorphism problem. So what does that mean you have to do? That means you have to say, okay, if I have a tree T, I have to define two groups, G of T and H of T. And if T has an infinite path, then my two groups should be isomorphic. And if T doesn't have an infinite path, then my two groups should be not isomorphic, right? Basically what this is saying is, if I could tell whether groups were isomorphic or not, then I could tell whether trees had infinite paths or not. And it's sort of a standard result that trees, so this is infinitely branching trees. It's a sort of standard result in computability theory that it's very hard to tell whether they have infinite paths or not. And in fact, right, so you're allowed to use two different groups, G and H. In fact, you don't really need that. The H is always the same no matter what T is, and it's only the G that changes, right? So how you actually construct the G and the H, that sort of gets into the actual group theoretic content. But this is sort of the logical side of what do you have to do. Now, of course, your maps G and H have to be relatively concrete, right? So they have to, you want the G and H to actually be continuous. If the G and H are continuous, then this is going to show that the isomorphism problem is sigma 1, 1 complete, right? So this is a non-classification result, right? If you look at classification results, you can get a finer picture by saying, okay, maybe they live in the Burel hierarchy, but at what level do they live in the Burel hierarchy? So again, we'll go back to this class of vector spaces. And it turns out the isomorphism problem is what's called pi3 complete, right? So it's pi3, and it's as hard as any pi3 thing could be. In particular, right, this means that vector spaces are not on top for Burel reducibility. They're not as complicated as structures could be, which makes sense, right? Because vector spaces are very simple things. How could they be maximally complicated? So, but we get like a specific level, right? Pi3, that's where our classification sits. And the way we see this, right, is the first thing we do is we say, right, to be complete, you have to actually be pi3. So usually when you want to show that something is at a certain level, you basically write down your classification and look at the quantifiers, right? So if we write it down, two vector spaces are isomorphic if and only if whenever you have a bunch of elements of one vector space, if they're linearly independent, then there's a same number of elements in the other vector space that are also linearly independent, right? This is saying the dimension of V is less than the dimension of W, right? And vice versa, you say the dimension of W is less than the dimension of V. And then we have to count quantifiers, right? So if you look, it says for every V, there exists W. And then if you say, what does it actually mean to be linearly independent? It means that for all scalars, right? So it's for all V, there exists W for all C, which is basically what it means to be pi3, right? So the complexity of the definition is going to mean that the isomorphism problem is pi3. And then to prove that it's complete, you have to do one of these reductions again. So the way you do reductions is you usually take something that you know is pi3 complete, in this case, the set of co-infinite sets, and you come up with a continuous construction, right, that transforms a set into a vector space. If the set's co-infinite, the vector space is finite dimensional. The set is co-infinite, then the vector space is infinite dimensional, right? And this gives a reduction, right? If you can tell whether a vector space is isomorphic to the infinite dimensional one, then you'd be able to tell whether a set is co-infinite or not. Right, it's continuous, so this is a simple, right, concrete construction, right, and it witnesses that the isomorphism problem is pi3 complete. So we basically what we did is we said, okay, we have this classification, right, and what we've proved is actually that it's the simplest possible classification. So you can think of this as saying there's no better classification of vector spaces than classifying them by their dimension, right? So there's no point, trying to do more research on classifying vector spaces. We're done. We've got the best thing you could do. Okay, so we talked about classification problems for a while. Let's go back to characterization problems. So say you have a class of structures and you have a property P, right? You can look at all the structures that satisfy this property. And we want to do the same kind of analysis on these sets. Where do they live in the Burel hierarchy? And the idea is if you've got some kind of characterization of the property, you'll get an upper bound on the complexity. And then you want to show that the complexity is complete at that level, so that there's no simpler characterization. Or if you don't have a characterization, then you want to show that the set of all things with property P is somehow complicated, like it's sigma 1 hard or pi 1 hard, something like that. So I'll give an example of a characterization result, and an example of an anti-characterization result. So for the rest of the talk, the groups are all going to be abelian. And there's this old theorem from Walker and Kahn that says that the integers have this cancellation property. So if the integers plus g is isomorphic to the integers plus h, then actually g and h have to be the same thing, right? So you can think of this as you can cancel the integers out. And right, this is some property of groups. Some groups have it, some groups don't. For example, the rationals have the cancellation property. The dyadic rationals don't have it. If you take infinitely many copies of the integers, this doesn't have it. Right? So some groups have it, some groups don't. And then you can ask, okay, which groups have this cancellation property? And sort of the only real known result is in a special case of rank 1 torsion-free abelian groups. So these are just subgroups of the rationals. And G has the cancellation property if either it's the integers, this is sort of somehow a special case, or it's got this relatively complicated problem, which is sort of it's called the endomorphism ring has 1 in the stable range. And there's this definition here which says, every time you have these elements, there's this other element, blah, 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 blah. Right? So there's obviously lots of group theory going to why this is true. But this is sort of a relatively complicated classification. And in the literature, people aren't really happy with it. Right? So people are even saying either they're not easily characterized, or some, like Estes Nome actually say, this problem is actually still open. Right? It's not solved. Right? This characterization is not a solution of the characterization problem. So what we want to do is come and analyze this. We want to say, what's the complexity of this set? And naively, it might be very complicated because you have to check all possible groups that you might cancel with and see that you do cancel. But using the characterization from the previous page, we can see it's actually pi04. And this is, again, a counting quantifiers thing. So basically, what you have to do is you have to represent endomorphisms. Those are all multiplication. Something's an endomorphism, right? So the multiplication by R map is actually an endomorphism only if R infinitely divides everything in the group. So you have to say something's even an endomorphism, you have to say for every n, there exists a g, R to the n times g equals 1. So you've already got 2 quantifiers. And then if you look at the property, right, you have to say for every f1, f2, g1, g2, so for every, there exists an h, right? And then you've got to actually say that things are in the endomorphism ring, that's for all there exists. So you sort of, the whole definition has for all there exists, which means that it's pi4. So you can say that the set of all things that are cancelable is a pi4 set. And then you want to say, okay, is this the best possible characterization, right? Could you actually push that down to something simpler? And to prove that, right, you have to prove a hardness result. So what I proved with TurboHo is that the set of cancelable groups is actually pi04 complete, right? So not only is it pi04, but it's as complicated as anything that's pi04 can be, right? And in particular, it's not sigma 4, right? So there's no characterization of the cancellation property that looks like there exists for all, right? So the simplest characterization is for all there exists, right? You can't sort of simplify the quantifiers in any way. Right, so the point is basically you've got this characterization, right? And we showed it's sort of the best possible characterization. There's no way of simplifying it. You're sort of done, right, in some sense. Now, groups of any rank, you can show that they're pi11 hard. We don't have any upper bound, right? So this is basically showing that groups of any rank, figuring out whether things have the cancellation problem is very, very hard. But it's still an open question whether there's an upper bound on how hard it is. The second non-characterizability result is going to be something in pure computability theory, which is a property called intra-reducibility, which was so to talk about this, it's sort of a pure computability, but I need to introduce a little bit of basic computability for people. Basically, you should think of something as computable if there's an algorithm for it, right? So a function is computable if there's an algorithm that computes the function. A set's computable if there's an algorithm that tells you whether something's in the set or not. Right? You can pass back and forth, right? So a function and its graph, right? So a function is computable if its graph is computable as a set, and a set's computable if its characteristic function is computable as a function, right? So whether we're talking about sets or functions, it sort of doesn't really matter. You can pass back and forth. And then if you have two sets, you can say that A is computable from B, right, or Turing reducible to B, if there's an algorithm that computes A using B, right? So you should think of the algorithm as trying to compute whether something's in B or not, and it's allowed to run on the computer, but it's also allowed to ask questions like, is 5 in B, is 6 in B, right? And it gets the answers, and then it can use those answers in its computation. So this means, right, if A is not computable, you might still be able to use B to compute it, because B might give you some extra non-computable information that you have access to. Right, so you should think of it as sort of like B knows what A is. And then you say, right, so this is sort of a definition from the 60s. An infinite set's called intrareducible if every time you take an infinite subset of A, that infinite subset computes A. So it's sort of a measurement of type of information redundancy, right? So even if you forget a bunch of A, right, but you still know infinitely much of A, you can figure out all the stuff that you were missing. And so the sort of examples are things that are quite redundant, right? So if I have any set A, I can take the set of all initial segments of A, right? So this is sort of the tuple, right? If I think of the characteristic function of A, right? It's like 0, 1, 1, 0. It's 0 if something's in, it's 1 if something's not in. And I take all the tuples that say, 1 is in, 2 is in, 3 is not in, right? Up to some finite tuple. And I take the set of all those tuples. This set of initial segments, this is intrareducible. Basically, if I miss a bunch of tuples, but I still have infinitely many, right? I might be missing the tuple of length 4, but if I have the tuple of length 7, the first 4 bits of that are the tuple of length 4, right? So from the tuple of length 7, I can figure out what was missing in the tuple of length 4, right? And then maybe I'm missing tuple of length 8. It'll have the tuple of length 10, and that will tell me what's missing from the tuple of length 8, right? So basically, if everything is coded like very, very redundantly. Another example, which I might skip for time, is if you have a C set, there's something called a modulus for the C set, and you can build intrareducible things using moduli, right? So maybe just for the computability theorists, right? If I take a C set and I take its modulus, and I take the image of its modulus, this is going to be intrareducible, right? Basically, because anything that dominates the modulus of a C set actually computes the modulus. So those are sort of the two examples of intrareducibilities. CE sets and their moduli, or in general, like self-moduli, there's sort of a general class of these things, or this sort of initial segment kind of construction with a lot of redundancy. So those are the two examples, right? The major paper in intrareducibility was one by Jockish in 1968. Maybe two example results so Lachlan, this was a result Lachlan proved that was in this paper by Jockish. There's a set that's intrareducible, but not what's called uniformly intrareducible. So if you're a computability theorist, that will make sense what that means. In, I think, 95, Siedepin proved if you have a set that's intrareducible and its complement is also intrareducible, then it's actually computable. So that's sort of the trivial way of being intrareducible, is you really had no information to start with. So there's a few results in this paper, but there's an open question that was still left open, right? So this is all the way back from 1968. Which is there a characterization of the intrareducible sets? And maybe your goal is, right, you've got these two examples of how to construct intrareducible sets, and there weren't really other ways of constructing them, right? So maybe your hope is that somehow by combining these two ways of constructing intrareducible sets, you could figure out how to construct them all, right? Or, you could come out with at least like some way of understanding why things are intrareducible. The other alternative, right, so that would be a characterization somehow of what it means to be intrareducible. The other possibility is a non-characterization result, right? That somehow intrareducible sets can just sort of happen to be intrareducible, not for really any reason you can write down other than they are. Right, so again, how do we solve this kind of problem? We say, okay, let's look at the set of all intrareducible sets. How complicated is this? And we know it's pi11. Right, so a set's intrareducible if for every subset of it, every infinite subset, right, there is a computable procedure P that produces back A. So, right, this for every b, right, that's a quantifier over infinite subsets, right? So it's one of these quantifiers that puts you up above past the Burel hierarchy, right? It makes you pi11. But then asking if there's a computable procedure, right? A procedure is just a finite list of instructions. That's one of these quantifiers that keeps you low down, right? So this is a pi11 thing. And if there was some kind of good characterization of introducibility, then the set of introducible things would actually maybe be Burel, right? It would be simpler than pi11. And what we show is it's actually pi11 complete. Right, so basically you should think of this as this is a non-characterization result, right? So there's no good characterization of introducible sets. Again, so how do we prove this kind of thing? So before, when we were proving these kinds of results, we used the fact that the set of trees with an infinite path is sigma11 complete. Now we're going to use some other well-known set, which is the set of well-founded linear orders. So these are linear orders that have no infinite descending sequences. And we're going to use the fact that these are pi11 complete, right? So we're taking something that's at the top level, and we're showing that introducibility is at least as hard as that. And so what you do is you say, okay, I'm going to take a linear ordering L. I'm going to construct from L a set. If the linear order is well-founded, then my set should be introducible. If the set is non-well-founded, then my set should be not introducible. And my construction of the set A should be relatively simple, right? So in this case, it's not quite continuous, sort of for silly reasons, right? If L was a computable linear order and you had a light phase continuous thing, then A would be computable and would automatically be introducible, whether L was well-founded or not. But basically, you use a single jump, right? So you're at the very first non-trivial level of the Burel hierarchy, building a cosine set in LA, right? But right, the point is that you're not allowed to ask, is L well-founded or not, right? You just have to look at L and construct it, and then it has to turn out that if L is well-founded, then A is introducible, and if L is not well-founded, then A is not introducible. Right, and so to do this, right, you have to understand something more about what makes something introducible, or how to construct new examples of things that are almost introducible but not quite, or things that are only just introducible. And you're introducing, right, so we had those two examples of ways to make introducible things. And the point is that you have to come up with a lot of new ways that were not just combinations of those two, right? So you're really introducing very complicated ways of making things introducible or not introducible. So that brings me to the end of the talk. So basically the takeaway, right, is that there's this analysis of classifications and characterizations, and it's a fruitful area of interaction between mathematical logic and other areas of mathematics, right, where mathematical logic really has something to say about things that other people actually cared about, right? So there are these problems that, classifying problems, characterizing things, right, like this group cancellation, that was something that people who did groups, who didn't do mathematical logic, right, they actually cared about that. And we brought in these techniques to actually say something that they cared about. Thank you.
Okay, thank you. Let's thank the speaker.